Hope you are doing well. So now we are in the final week of this course, and this week we are going to mainly talk about surface integrals. Okay, so there will be some important theorems which will be discussed in the second part of this lecture. So surface integral, so what you need to do is you recall the notion of line integral. You know what we did, we started with defining the arc length, and then with respect to that arc length we could integrate functions over any given curve, isn't it? And then we could define integral of vector fields over curves and so on. So we are going to do the same here. So instead of the arc length, now we will be dealing with surface area of a given surface, correct? So once I have the surface area component, then I can define a corresponding notion of surface integral, which will allow us to integrate a given function over the surface. Okay, and surface area we have already discussed, so it will be just recalling several things, and then of course there are going to be some new definitions also in the process, and we will slowly try to develop today the notion of surface integral. All right, so let us see. So as in the case of curves, we first define what is a parametric surface. Okay, so you consider a domain in R2 and consider a vector valued function. So this function is defined from D to R3. So this is taking value in R3. Okay, and the component functions are written as X, Y and Z, and these are functions from the domain D to real line, isn't it? So many a times we will write this vector notation, or many a times we will just write X equal to a function of two variables, and then y equal to function of the two variables or the parameters. Similarly z equal to. Okay, we have seen some particular examples of this. Okay, so this is, we will always refer to this equation as well as this equation as the parameterization or the parametric of the surface. Okay, all right. So remember that we had seen surfaces as graph of some functions, isn't it? So that is the first example, and here what is the parameterization? So x and y, they just remain the same variables, and the z component is varying according to a given function, isn't it? So that is the parameterization. And for example, another example is given over here, the sphere, for example. Okay, so how does one describe a sphere? We can use Cartesian coordinates, but we also had the spherical coordinates. So if you look at those coordinates and imagine the function, so this is the x component, this is the y component, and this is the z component, isn't it? So this theta and phi, these angles we had already discussed, so I will not go into the notation again. And they vary. This is the angle with the positive z axis. This varies between 0 and pi, and this comes from the polar coordinates in the xy plane, and this varies, theta varies. So this radius here is 1. Okay, so this is going to give you a sphere centered at the origin and radius 1, isn't it? So the parameterization here, u and v are basically theta and phi. Okay, and several examples you can write down, but one important class of examples we can express as parametric surfaces. They are called the surfaces of revolution. Okay, so what we do basically, you imagine any curve. Okay, so I am going to give you an example. So let us look at some examples here. So think of this line segment. Okay, now if I try to revolve this line segment around, or rotate this line segment about this axis. Okay, so then what I will get, you see what I am just doing, this is the endpoints are fixed and this is rotating. So you will see that you are going to get all these lines here, and this is going to give you a cone surface. Okay, this is a cone because the base will give you basically a circle, and then these things will give you these slanted lines all over, and this point is fixed, and you are moving or rotating this thing like this. Similarly, you look at this picture. If I look at this curve and try to rotate it, okay, about this vertical line, then I'm really going to get something like sphere. Okay, so these surfaces which are obtained by revolving or rotating a curve about another line or another curve, they are called surfaces of revolution. Okay, so these surfaces can be expressed as parametric surfaces, and the idea is very simple, because what is happening, that each, so this is the the part which is revolving, and you see around this, for example, if I take a point here, then this is going to give me a full circle with the same height or same distance from this point. So this is the whole idea, that if I start if I consider a curve by equal to fx, let us say this curve is defined on the parametric interval a to b, and we want to rotate it about x-axis. Okay, so this is the situation here. So I have a curve, so imagine the curve is like on this, and I want to rotate it about the x-axis. Okay, so at each point of the curves we have to trace it, that how does it go around the x-axis, correct? So if I take a point here, that is going to be some by equal to fx. So now this fx is going to go a full circle. Okay, and that means this is what we are doing, that x remains, because x is the, we are rotating about the x-axis, so the points on the axis, they remain the same, and the by coordinate is going to move, because we have to see that what is the height. So height is going to be determined by the value of this function, or this by equal to fx, and this is going to give you a full circle. So this is the cosine theta and then the sine theta, isn't it? So this is how you can express. So this is precisely the parametric equation. Okay, so here we are doing it about x-axis. You could have done it about y-axis, or you could have done it about x equal to y line, or anything. You pick a curve, and then you can try to rotate it and generate a three-dimensional surface. Okay, and such things can be expressed as parametric surfaces. Okay. So now we need to basically define what the notion of surface integral. As I said, what we are going to require, the surface area component. Okay, which we had already discussed, but whatever we discussed, that was a particular case when the surface was given as the graph of a function. Okay, so now we are going to have the same idea, same expression for the surface area for parametric surfaces. Okay, and if you remember, you go to the lecture where we discussed the surface area. How did we do it? I will actually first show you the surface area, this thing. So we had a function of two variables which was defined over some domain. So this was the situation, that this is the domain and this is the surface. So our goal was to find the area of this surface, isn't it? What we did, we looked at small rectangles in the domain, and then their corresponding images on this surface. Okay, and then we tried to approximate them by the parallelograms, isn't it? And in doing that, so basically you took a corner of this and then look at the two tangent vectors. So if you look at their cross product, that is going to give you the area of this parallelogram, correct? That was the whole idea. So same thing is going to happen here, and we saw that this the area turned out to be this function, isn't it? So we are going to have precisely the same idea. Now the surface is given by the parametrization. Okay, so let me just go about it. So you consider tangent plane. Okay, so we are going to look at the tangent plane. Look at this surface. So suppose this is the surface given by a parametrization parametric equation R of u comma b. Okay, the one which we have been writing. So now we look at a point here, correct? What we need, we just need to determine the tangent to the curve where which is the curve fixing x, and then curve fixing another component y, and then you look at the tangent and you get approximation to the surface area component by considering these parallelograms, isn't it? And then their areas. So here that the tangent are just going to be the partial derivatives. So for example, this curve is c1 and this curve is c2. Okay, this is, so this curve, how do you get? You are fixing one variable here, correct? So c1, this is the curve c1 and this is the curve c2. Okay, so this curve basically is going to be for a fixed value of x, and this curve is going to be for a fixed value of y. So what you are going to get, the tangent vector here is, so here x and y, this would be thought of as u and v, isn't it? So if you just compute the partial derivatives of r, this vector valued function, okay, because these component functions, they were functions of two variables, so that is why you have to compute the partial derivatives. So you fix a point p naught, okay, on the surface, and try to compute, okay, let me just highlight it. So this is the point we are taking, and look at these curves. Okay, so these curves are precisely, I mean, by the C1 is the curve by taking the value by a constant, and C2 is the curve by taking the value x constant. This is the same thing which we did while computing the surface area. Okay, and then we look at the tangent vectors. So these are the tangent vectors to C1 and C2 respectively at that point. And what is the tangent plane? So the tangent plane is the plane which is going to contain these two tangent vectors, isn't it? And the normal to this tangent is given by the cross product. So all this we had done, so that is why I am not spending too much of time. So you imagine this here, and then imagine a plane which is tangent at this point, and then the normal vector is going to be given by the cross product of these two guys, correct? The REP and RU. Okay. So we will always have this these surfaces, whatever surfaces we are going to work with, we will assume that the surfaces are smooth, okay, which means that the normal vector is non-vanishing. Okay, so always keep in mind that we are going to work with smooth surfaces. So now the surface area component is going to involve, because this is if I take the magnitude of this, then we know that the area of the parallelogram determined by these RU and RVs is going to be just the magnitude of these guys, isn't it? The cross product. So that is what we are going to, okay, this is precisely what I had just said. And what you can do is, okay, let me first complete this. So okay, this is the definition. Previously we had a discussion. So now when you say that what is the surface area of a parametric surface, so you need to make some assumptions, that you start with a smooth parametric surface given by this parameterization, okay, and then the domain is a domain in R2, and this also is important here, that we cannot have like multiple values. So here we are saying that S is covered only once as U and V ranges. So different we should not be mapping several things to just one. Okay, that is going to create problems. So we will not have that situation. Then the surface area is defined by this, precisely the same formula which we had for the surface area of graphs of functions. Okay. And this component, instead of this we had that square root of 1 plus fx square and then fy square, isn't it? And if you look at that particular surface, this is the particular case, then the tangents are precisely these vectors, and the cross product, if I compute and its modulus, I am precisely going to get this. Okay, so that was kind of a particular case of a parametric surface. When we have any parametric surface, okay, with these assumptions, then the surface area can be written down or can be computed by this formula. Okay, so you know that how to derive this formula. I had just also given you the idea today also. Okay, so this is the surface area. Now once I know the formula, or how does one compute the surface area of a parametric surface, then what I can do is, now I can extend this definition to incorporate surface integral, or I can define surface integral of functions over these kind of surfaces. Okay, like we did in the case of line integral. Okay, but there are going to be some new definitions also. So this is very straightforward, as I just said, that surface integral of a function, assume that the function is continuous, because otherwise integral may not make sense and so on. So we put some minimal assumptions here, and this is precisely you evaluate your function at the surface, and then this is the surface area component, isn't it? So this is precisely the same definition as, I mean, the idea is precisely the same. Okay, for example, you can work out one example. Okay, so consider this. So here the function is f of x comma y comma z is just z, and s is given to be the upper half of the sphere centered at the origin and of radius 2. Okay, so you write down the parameterization. Okay, here the parameterization is not given, so write down the parameterization of this surface and just pull this formula, and of course you have to compute RU and RB and then the cross product. So you know it's going to involve several steps, but those things you already know how to do about it. Okay, so you know whenever you have to deal with surface of a sphere, it's always good to, you know, go to the spherical coordinates. Okay, so please be careful. I often make mistakes while, you know, doing these things, and just see that what was the radius is 2, and this was upper half of the sphere. So here the phi, this angle is only going up to pi by 2 because we are only in the upper half. Okay, and this is of course full. So you compute this r phi. Okay, there is a mistake here. This should have been theta. Okay, so r phi cross r theta. So for that you have to first compute the partial derivatives of this with respect to phi and theta, and then compute the partial derivative and see whether you get 4 sine pi, and then just you know, put it in the formula. So evaluate the function at this curve. Okay, that means x is this, y is this, and z is this. So f involved only z, so this is precisely the z component, and then this is the surface area component, and what you get is just this integral of sine and cosine. So please verify this, but you know, because you know I make mistakes, as you have seen in the past also. Okay, so this is precisely the same motivation to come up to the surface integral of functions. Okay, now we are also going to have surface integral of vector fields. Okay, but when we go to vector fields, there is going to be a sense of direction also. Okay, so for example, for curves we had a positive orientation and negative orientation. Okay, so similarly for surfaces we need to develop a notion which you know gives us a sense of direction. Okay, so we are going to do that. So in the process we will consider only some particular type of surfaces. Okay, yeah, this is what I just talked about. So we will basically, we need to define orientation of a given surface. Okay, this is what we need to do, and we will, you know, call them oriented surfaces, and then whether they are positively oriented or negatively oriented, so that we will specify. Okay, so two things. First, we will consider closed surfaces. So the closed surface is simply you know, a surface which encloses a region. Okay, okay, so imagine the surface of a sphere, correct, or I mean ellipsoid and so on. So they are going to enclose or bound a region, a solid region in R3. So that is what, as any such surface we call a closed surface. Okay, all right. The important thing is we are going to consider surfaces that have two sides. Okay, so now you have to imagine, you know, you have to imagine a little bit. So I have drawn here, not drawn basically, I have taken two pictures from the book. This picture you might have seen, this is called the Mobius band or Mobius strip. Okay, so look at the difference between this and this picture. Okay, so this is like a sheet of a paper which is slightly folded. So this is one surface and this is another surface. Okay, so here you know, you have a sense that either you are on the upper side of the surface or on the lower side of surface. So you know, these arrows here are basically pointing this thing only. So if you are on this face of the surface, then you are always, your head is always up, isn't it? Whereas if you are on the inner surface or the downward surface, then the arrow is pointing downward, isn't it? But here you see, if you are on this surface, okay, so if you are at these points, this is, you know, the arrow is pointing in this direction, but the moment you come here, now you see you have come on the outside. So you started, let's say here, okay, you can start, this is the point, for example, this is a point marked over here. So you start here and then start moving the, you know, this is the inner side of the surface, and start moving along the surface, and then you see, because of this, now you have come outside. So this guy you know, has only one side in a way, okay, whereas here this is not happening, that if I move along this surface, I will reach the boundary, and if I have to come down, you know, I have to I will fall off of this, and you know, I will not come to the downside. But here this is, I mean, you can move very smoothly, and from outside to inside and inside to outside, okay. So when we are going to consider surfaces in this course, we will consider surfaces of this type, okay, namely the surfaces which have got two sides, that the outer side or the inner side, okay. So this is one thing, and once I have this, then I am going to have tangent planes at every point, okay, and at every point there is going to be a tangent plane, and then there is going to be a normal vector. So this is precisely that, the normal vector. So the normal vector is going to point outward, and then the negative of that is going to point inward. So basically we are going to look at surfaces which have two sides, or which at each point have two normal vectors. One is pointing outward, one is pointing downward, okay. So this is what we are going to refer to such surfaces as oriented surfaces. Let me you know, write the concrete definition. So let S be a surface that has two sides, okay, and it has tangent plane at every point, okay. So this is some regularity assumption. Of course, I mean, if you are at the edge of the surface, that is exempted. So this assumption makes sure that at every point you have two normal vectors. This is what, the normal vector n, and then the negative of that, okay. So if we can choose unit vector or unit normal vector n at every point of the surface, so that this n varies continuously over S. So what does it mean? Look at this, okay. If I start moving on the surface, then the normal vector will also move. So what we are saying, that if we have a surface on which I can choose this n, this vector n, or this vector is continuous, you know, then we say that the surface is oriented surface, okay. So this all the surfaces which we are going to work with, we are going to be simple enough, okay, like you know, coming from sphere, or maybe some flat surfaces, I know, conic surface, and cylindrical surface, and those kind of things. So you know, these assumptions are always made and we don't have to, you know, verify them. All we have to care about the orientation, okay. So orientation is defined for the closed surfaces, okay. So we say that a closed surface has positive orientation if the normal vector, okay. Now we have started with oriented surfaces. So we are saying that a closed surface which is orientable has positive orientation if the normal vectors point outward, okay, from the region enclosed by S. So what you do, you have a closed surface, it's going to enclose a solid region, okay. So if the normal vector is pointing always outward from the region which it encloses, then you call it positively oriented surface, okay. And if it is pointing inward, you know, in the solid, then you call it a negative orientation of the surface, okay. So this is one illustration of this. So this is a sphere, okay. So this is the surface, and it encloses this the region inside this sphere, so this whole ball. So this the normal vectors are pointing outward, means we are considering positive orientation. If the normal vectors are pointing inward, then we are considering the negative orientation, okay. So this is the convention, or this is the understanding we should have, okay. Once we have this, now you know, we know that how to compute these normal vectors, because we will require them, as we did in the discussion of surface area. So the normal vector is always given by this, correct, because the tangent plane is basically determined by RU and RB, and then the normal is going to be given by the cross product. Okay, and then we always consider the unit normal, so we divide by the, and this is possible because, as I said in the beginning, we are always going to consider smooth surfaces. So this guy is non-zero. Okay, so the unit normal vectors are going to be given by this. Okay, all right. So in particular, when you have our previous situation that the surface is a graph, then so this is the surface you are looking at, and we know what is when we started discussing about these surfaces, and then we saw that the tangent the gradient vector gives you the normal to the surface. So because we are considering the unit normal, so basically you consider, so the here n, which is this, and this also is written like this for this particular case. Okay, and because this is given z equals to g of xy, so you can precisely compute in terms of the partial derivatives of this function, isn't it? So here this is k has only component 1 because this is just the graph. Okay, and this also tells you something here, the constant or the component function here is constant, and it's a positive constant. Okay, so this is basically telling that I am going to look at in the k direction, the normal is moving in the positive k direction. Okay, so this is why we say that component is positive, and hence the normal vectors are going to point outward. Okay, so this is a positive orientation. If you want the normal pointing downward, then you have to replace n by minus n. Okay, so these are some things which you have to keep in mind about the orientation. Okay, so now once we have this notion, what we can do is we can define surface integral over vector fields of vector fields over given surfaces. Okay, so as always you would start with a vector field, okay, which is continuous. That means all the component functions are continuous, and it is defined on an oriented surface S, okay, with unit outward normal n. Okay, so this n is always going to refer to as unit outward normal, and sometimes we just say that it is given with positive orientation, or sometimes you say that upward unit normal, and so on. It depends. So the surface integral of f of this vector field over S is defined by this. So this is the notation that you write f dot ds. This is the this is the S is also a script here because this surface is given by a vector equation. So this is going to be f dot n. Okay, this f is, so this is the normal component, and then ds is the surface area component, isn't it? So all you have to do is you evaluate your vector field at the surface, and then compute the normal vector, which is going to be this, and this is the surface area component. Okay, but you see these two guys are going to cancel each other, so precisely all you have is this, and this is the domain of the parameters u and v. Okay, so this integral you just first compute the dot product, and you can compute the surface integral. Okay, so this is precisely in the same line of arguments which we did in the case of line integral, isn't it? It's precisely the same thing. And as there, I mean, this is also called the flux of f. We had discussed this idea when we were discussing the divergence form of Green's theorem. Okay, so this is also the same idea over here. All right, so let me give you a quick example. Actually, this example is more important than what we have discussed so far, because once you understand this example, you will get the crux of the matter, and you will be able to compute surface integrals. Okay, so this example, be very careful. So let us have this vector field. Okay, here the component functions are y and z, and one component is 0. They are very nice, and this is given over a positively oriented surface S. Okay, and what is the surface? This is surface given by this paraboloid. Okay, and this disk. All right, so be careful. As I said, this is y equal to something, not z equal to. Okay, So you have to draw this paraboloid. So its picture is here. Let me first, so this is the picture of the paraboloid, okay, and y is varying from 0 to the 1, okay, and then disk. So disk is x square plus z square less than equal to 1, okay. So this is in the xz plane. So this is, I mean, you look at this face, this is the disk we are talking about, okay. So this is precisely z equal to the y equal to 1 here, over here, okay. So just, you know, stare at this. So this whole thing, the surface is basically this whole thing, okay, this paraboloid and then this disk, okay. So what is happening here, what is happening over here is that your surface is made of basically two things. One is the paraboloid, and then, you know, there is an edge here, and then the other surface is this disk, okay. So basically if you want to compute the surface integral, okay, you need to consider a surface with positive orientation. So that positive orientation, now on this, you know, we have to take the solid which is the inside part of this, and then see the normal vectors. It needs to point always upward from that solid, isn't it? So the normal is going to be like this here. I mean, this is not even a line, so it's like this, correct? So it's going to point like this here, okay. And if I am on this, then it's going to point like this here, okay, okay, because the solid enclosed by this surface, the normal is going to point outward of that, isn't it? Okay, so this is what you have to always keep in mind, you know. So first we need to observe that the surface is union of two things, okay. So as we always did, whenever there is an integral, if it is defined over union of two things or many things, what you have to do, you have to compute the integral over each piece and then sum them up, isn't it? All right, so this is what we will do. So we will compute the surface integral over S1 and then surface integral over S2 and then add them up, isn't it? Okay. And other thing, as I said, yeah, this thing. So you see the disk is like, you know, it's just putting a cap on this opening. I mean, if you think of this as a bowl, and then you are just, you know, putting a cover up or lid up on this. So this makes as a closed surface, okay. See, if this disk is not there, then this surface is not closed. It's not going to enclose any region, okay. So I need to do this because, you know, in order to understand the positive orientation here, I need to consider the solid enclosed by the surface, okay. And the surface is made of two things. So now I have a solid surface, and you also know that it is with positive orientation. It needs to be considered, okay. So what we will do is we will evaluate the surface integral on both the surfaces and add the results, okay. But as I said, we need to be careful that we always do it with positive orientation, okay. So S1 and S2, they come together with positive orientation, okay, and that will determine the unit normal on S1 and S2, okay. So we need to okay, let us first consider the surface S1, which is part of the paraboloid, okay. As I said, the paraboloid is y equal to x square plus z square, okay. It's not z equals to, so that you have to keep, okay. So that's why its opening is you know, in the positive y direction. So this is I have been, you know, telling again and again that we need to be careful while choosing the normal vector or while computing the normal vector. So when the surface is given by a function, we know that we need to consider the surface given by, you know, this by minus x square minus z square. So this is precisely the situation which we just discussed, okay. Yeah, I mean, this I have just highlighted just to, so that you are careful, you know. So the normal vector is going to be given by the gradient, isn't it? So the gradient of this, when you compute, it's easy to write down. So there is going to be partial derivative of with respect to x, then y, then z. So you have this, and then to get the normal vector, you have to divide it by the length of this or the magnitude of this, okay. But you see yeah, it's written over here that this has positive j component, Okay, look at the j, because the normal vectors, the normal vectors, as I said, the normal vectors are going to be pointing in this way. They are not going to point in the positive y, but that is what it is happening over here. So what we have to do is, because we are considering the positive orientation, so the normal vectors should point outward from the region, and hence we need to consider the negative of this direction y. So that means we have to consider the normal vector as the negative of this gradient. Okay, so this is very important. See, the negative here doesn't make any difference, but here it makes a difference. Okay, because the positive bidirection is this, but that is not going to give me, because if the normal vectors are pointing in this direction, then I am actually at points I will be pointing inward. Okay, for example here I will be pointing inward the region. So that is not the case. So that is why I have been telling you, like, you have to be careful. So in order to determine this n, you have to understand that what is the positive orientation on this surface. Okay, so you do that, and once I have this, then everything is just you have to compute f dot n. Okay, please compute these things and verify the, so your parameterization is x equal to x, and then y equal to, because this is the graph of y equal to something. Okay, and then z remains z. So f dot n you compute, and then the domain is going to be in the xz plane. Okay, and just apply the definition. F dot n you have computed, and all you have to do is just evaluate your function on the surface, and then look at the cross product here, take the dot product of these two guys, and then you get this. Okay, now domain, what is the domain here? The domain is precisely this, because this whole surface, if I look at the projection in the xz plane, what I am going to get is just going to get a disk, isn't it? So I know that here this, actually I should have written here d1 and then d1 here also. There is a typo here, because I have called it d1. Okay, for some, because s1 and then d1, probably that is the reason I wanted to do is okay, but these things you can please correct. So this is a disk of yeah, I mean it's going to be disk of radius 1. So precisely you have to write down the, when you integrate over a disk, what you do usually, you consider the polar coordinates. Okay, so this is what I have done. So these calculations I always omit, because you can do it without any problems. So this is your double integral now you need to compute. Okay, and the region is a disk, so or the domain is the disk. All you have to do is just write down x equals to r cos theta, and z equal to, here this is not y equal to, but z equal to r sin theta, and just find the value of this integral. Okay, so this is only one surface so far we have taken care of. Now the second surface is this. Okay, now as I told you here, that whatever we have here, the we need to consider positive orientation, so we will consider the normal vector which are pointing this way. Okay, so all we need to do is, now this is disk, is simple. Yeah, so look at the picture, as I said, and then the unit normal vector is going to be always given by, because this is a flat disk, and then the unit normal vector is always given by the positive bidirection. So you have this straight away. I see here I have written d2, but here not, so you please correct these things. So and yeah, so by ds here, because by is just 1, so this guy doesn't have anything, any function over here. So this is precisely the area of this disk, which is pi, because the radius is 1. Okay, so you got pi from here, and you got minus pi from here. Okay, so the total integral is going to be 0. Okay, this is happening because you had this positive orientation. Okay, if you mix up with the orientation on this surface and that surface, the answer will change, and it will make it will be a huge mistake. Okay, so you need to be careful. Okay, work out some more examples, and now what I will do is, in the next part of this class, I will talk about further further some important results which will be kind of analog of the Green's theorem. Okay, so now we will have some analogous results for triple integrals. So basically what we will have, as you saw, that we have surfaces and they are enclosing a region. Okay, so if you want to find the integral over the solid region, so that's going to be a triple integral, and we will have results which will tell us that that triple integral over a region can be represented by a double integral or by a surface integral. So this is precisely the same thing, that the surface, we saw that the integral over surface can be written down in terms of the curve, which is the boundary. So similarly, if I have a region, the boundary is going to be a surface. Okay, so the same idea in higher dimension or dimension 3, we will have some theorems, and they will be called Stokes theorem and then the Gauss divergence theorem. Okay, that will be in the next class. See you.